everyone, my name is Kevin Choi, and today I will talk about the applications of group theory. Before moving on to all the applications of group theory, I'm aware that most of you guys are not aware of what groups are in group theory. So I'll just define to you guys what groups are first. So group is a mathematical structure consisting of a set G and a binary operation. Like for instance, like a dot satisfying the following properties, what we also call the axioms. So first of all, it should satisfy the closure. So that means that for any elements that A or B that is in group G, that means that for instance, the product or A times B should also be in G as well. And here I just made a product as an example of a group. There could be like many other types of group as well, not only the product. And another way is the associativity. And here, for instance, in the multiplication, the operation of the multiplication is associative. So, for instance, the A times B, parentheses times C, of course, equals to A times parentheses B times C for all A, B, and C that is inside G. And next, a group should have an identity element where in the case for multiplication, it's defined as 1 because as you guys know, for any number or integer, any integer times 1 equals to itself. So that makes the 1 an identity element in the group of product. And lastly, the last one that should satisfy is the inverse element. So which means that for each element A is inside G, there should exist an element A to the inverse, which is called the inverse element, such that A times A to the inverse should equals to the identity. And for the subgroups, I'll explain this a little later in the next slides too, but a subgroup is a subset H of a group G is a subgroup. It's like same thing as like the concept of set and a subset, where there's a subset H inside the set S, set G, and here it's like a subgroup S inside the group G, with having all the operations of G as well. So I'll just talk about more definitions relating to group theory, and knowing all these definitions will be essential for some of the proofs or some of the applications I'll show you guys in the next slides. So first of all, the order of an element. I'm not too sure how many of you guys have learned number theory to like a further extent, but order of an element is the smallest positive n such that x to the power of n would equal to the identity. So one example I can talk about this is, for instance, if the order would be like, for instance, like the phi of n, for example, in the Euler's formula. And then another one that we have is that the order of the group is that for a finite group G, the order of G, we just put an absolute value on it to express it as a magnitude, is the number of elements. So for an infinite group, the order is infinite. And next, we have a cyclic group, which is a group that can be generated by just a single element. And one example I have here for you guys to understand it better is that the odd numbers in general, which is x is 1 mod 2, because if you continue multiplying the odd numbers itself, the results are going to be odd numbers. There won't be any different changes, right? So that'll be one example of a cyclic group. And lastly, what I'd like to talk about is isomorphism. This one, I won't say is very necessary to understand what I would like to talk about in the later ones, but I'll explain it anyway. So isomorphism is when two groups of G and H are isomorphic, which is similar to congruence if there exists a bijection from G to H that preserves the group operation. And one good example I have here again is the Euler's phi function, which is Euler phi A times B would equal to Euler phi A times phi B for all A and B that is inside group G. So I would like to extend what's in subgroup here. So the subgroup H, I'll move on to this slide again. So that H should be a subset of group G such that it all satisfies what G has. So what I talked about, the four essential axioms above, here is that the closure, associativity, identity element, and the inverse element here, right? So the subgroup H should all have these four different elements as well. and it should be part of G to make it to become a subgroup. And I'd just like to give an example of a symmetry group of which is S3. And I just defined S3 a group of all permutations of three elements under the composition of permutations. So for example, I put the multiplication table and I put that S3 is not a abelian group, and for I'm pretty sure most of you guys won't be familiar with the term abelian, and this is like similar to a commutative group. So I'm pretty sure all of you guys know what a commutative property is, right? So commutative group is a group that satisfies all the four axioms I talked about earlier, but it also should satisfy the commutativity, which is for instance like A times B equals to B times A. And in a multiplication table to identify whether a some kind of group is abelian or not is to just check by whether the table is symmetric or not by the diagonal. And as you guys see here, the diagonal here shows that the table isn't symmetrical about it. For instance, there's like 1, 3 here, but there's like 1, 2 over here, and so on. And next, I'll just like to talk about the subgroups of S3, and building upon this, this will later result to like some kind of like formulas, for example, like the Lagrange theorem or like other like group theory like stuff here. So first of all, order one is just E, which is like the identity element. And then we have the order two, which is E and like groups of like 1, 2, 1, 3, or 2, 3. And I'll just give you guys 1 minute to think about like what the order three would be. Okay, so now it says the order three here is basically like what happens if there's like three different elements in a group. So just like E, 1, 2, 3, and 1, 3, 2, because E is an identity element, and these are like different types of like order three elements. And then lastly, the order six will be like the combination of order two and order three elements here, the, and then this will help us understand like some of the patterns here. So which is that the orders of S3 subgroup all divide 6, which is the order of S3. So this makes us to give a conjecture that if H is a subgroup of finite group G, then the magnitude of H will be divisible by the magnitude of G. This will be known as the Lagrange theorem, which is an essential part of group theory. So now I would like to prove the Lagrange theorem. And the proof here that I put here is very rigorous. So before I explain it, I'll give you guys like 10 or 15 seconds to take a look at it so you guys can try like grasp it like a little bit first. Okay, so I'll continue. So first of all, we want to divide G into disjoint cosets of size n, right? So for an element such that X is under the subset G, the group G, we should consider that the set XH such that it has every like element of like XH such that H is inside the subgroup of H. So we first show that the XH must have n elements. So that means that if X we have H1 all the way to Hn, right? So if we just pick two random elements, which is XH1 and XH2, then what we can do here is that in group theory, we can't just like divide them. So what we instead do is that one of the axioms is that it's the inverse axiom, right? So what we do here is that we multiply the inverse of the two. So we have to multiply the x to the inverse on the both sides, which makes h1 equals to h2. Then what we do here is that we show that if there is a no common intersection between the x1h and x2h, then we can also identify here that the x1h equals to x2h. This means that there exists such H1 and H2 in the subgroup H such that H1 x1 H1 equals to x2 H2. And here, what I explained above, we should multiply H1 inverse on both sides. And here we have the x1 equals to x2 H2 H1 to the inverse. And this makes that any elements of x1 H equals to this. And since H is a group, we can also define that H1 to the inverse is also in the subgroup H, and H is a closed group. So which means that H2, H1 to the inverse H is also in H as well. So therefore, any element x2 H is in the x1 group H and vice versa as well. So this makes the x1 large H equals to x2 large H. That means that G can be divided into any disjoint sets of size n, which makes n divisible by the magnitude of G. And here n will be the magnitude of H because they'll be from H1 all the way through Hn. So, so now, by the Lagrange theorem, I'll just try to apply to prove some famous theorems. I'm pretty sure all of you guys know what a Euler's theorem is, hopefully. So let's try. So the claim is that let's have the phi n be the number of integers k such that there is like integer from 1 all the way through n, and GCD k and n are like co-prime. And so for all x such that GCD xn is 1, that makes x to the power phi n is 1 mod n. So we have un be the group of units of mod n under multiplication. This is like the same thing as having all the numbers from 0 all the way to -1, which is like all the numbers that is under mod n. And here, by definition, we have the magnitude of un as the phi n, because not only that the group of units that we mean here is that all the numbers that also has to be co-prime to n as well. And now we should consider the cyclic subgroup generated by an element x. And in group G, we have from the identity element all the way through the x to the power order x minus 1, since what we showed in the previous slides above, that the x to the order x should always equal to 1 mod n, which we defined in slide 2. And if you guys don't understand this continuously, you guys can like go back to like the previous slide so you guys can maybe understand it. So here we have the magnitude of G equal to the order of x. Since the magnitude of G is how many elements there are, and we can count from x to the -2 all the way through x to the order x minus 1. So here we have G as a group because x to the m times, for instance, x to the n equals to x to the n plus 1, and we have E inside G, and we also have the inverse too, which is x to the n to the -1 equal to x to the order of x minus n, which satisfy all four different types of the groups. So by the Lagrange theorem that I explained earlier, we have the magnitude of G is just by the magnitude of un. So we can simplify this as the order of x divisible to the phi n. So this means that the phi n could be expressed as like some kind like k times the order of x, such that like k is an integer. So what we can have here is that x to the phi n equal to x to the power of k times order of x. And if we like take out the k, we have x to the power of order of x, which would be equal to the identity element by definition. And then we'll have the identity element to the power of k equaling to the identity again. Next, I would like to talk about the second and the last application of this one, which is that if that the magnitude of G is P, and let's say P is a prime number, then G is cyclic. And all these terms I talk about, like cyclic or like the order or like all these things, I all explained it in slide 3 as one again. So like all these the definitions I have provided in these slides are very essential in solving these problems under here. So now let's start the proof. And if you guys want to prove this on your own, you guys can maybe like stop the video and try it on your own before you guys like solve the problem actually. So since prime number is always greater than 1, we can also have that the magnitude of g greater than 1. So that means that there exists an element x such as the order of x is greater than 1. And by the Lagrange theorem again, we get that the order of the subgroup generated by x divides the magnitude of g, which implies that the order of x is divisible by the g or p here, since the magnitude of g is equal to p. And since that happens and the order of x is greater than 1, this means that the order of x has to equal p anyway. So this implies that every element in G, it could be written as x to the power k for some integer k, which simplifies and therefore concludes that G is cyclic. And before ending the presentation, I'll just like to talk about the reminder. And this hard content relating to the application of group theory is one of the lessons I valuably learned from a rigorous program I attended this summer. So all these content here may seem hard at first, but as you guys like continuously grasp it, understand it, it will be much easier and like much more convenient to like understand. And this is where I got all of my references. Thank you.